All right, everyone. We are ready to begin. One quick note, I've gotten a couple emails about lecture videos. I have updated all the ones for this unit to our playlist, but also just know that if you click on my name on any of the videos and go to the lives, they're all immediately available there. If that link is embed somewhere on the bright space, you should be able to click into that from any of the existing videos. And so all you have to do is check the dates there. So that other updates, I will make sure that the practice exam is available by tonight for our upcoming exam, so that you can get started on that, so that I can check in on how we're doing. But otherwise, we are going to finish up thinking about our synapses. Okay. So in order to do that, this is going to be kind of inextricably linked with our understanding of graded potentials. So I want to do a quick review on some of the points about those from when we focused in on them at the beginning of this section. All right. We're going to have a couple questions. These are going to be kind of quick. Just want to remember what a graded potential is. Those are fast, but we have a couple of things to review to go in on. Okay. So yes, a graded potential is a small change in the membrane potential. So this was when we were talking about stimuli coming in, the dendrites, the cell body, making small changes to that charge inside the cell. Separating it off from our action potentials, which are large. Is faster than I thought it would be. All right. So yeah. So we're talking about positive charges entering the neuron, because graded potentials really do happen when we have a stimulus into the membrane and therefore changing the movement of ions. So if we have positive charges coming into the neuron, so the sodium, things like calcium, that membrane potential inside our neuron gets closer up to its threshold value, so it becomes more likely to fire off an action potential. possible. The double negative is something to pay attention to, but we look pretty good. Okay, so when a membrane potential goes up, and specifically when it's becoming less negative, right? Like when we have sodium flow into the cell, adding positive charges coming up from -70. This is called a depolarization. Why we have the depolarization phase of our action potential, but we might also say it about a graded potential. We might say that it is depolarizing. We can do the reverse too. So positive charges are leaving the neuron. Yeah. So if positive charges leave the neuron, like potassium, this means that we are getting farther away from our threshold value. It's becoming harder to fire off an action. So we can make up for those positive charges that we lost, and then also have enough to depolarize to threshold. Got a word for this? Great. Yeah, if you become more negative than the resting membrane potential, so resting membrane potential, -70-ish, we go below that, we consider this a hyperpolarization. So we become more polarized, more negative. Okay. Thank you. A couple of these. Only these first two are true. So graded potentials, it's all about adding them up, adding together multiple signals. We can add them up in time. We have one stimulus come in, doesn't quite fade away before we have another stimulus come in. We can add them together that way. Or we can add them up in terms of space. So if we have two signals come in at the same time in different parts of the neuron, we're going to have to add together parts of their charges, which is another way we can add them together. So we add them together to get to threshold. Okay? So they're not always the same size. So we can have strong stimuli and weak stimuli. That's a difference from the action potential, which is always the same size, always goes to +30, falls back down. These graded potentials aren't always positive, so we can have depolarizations. We can have positive ions come in, but we can also have graded potentials that are hyperpolarizations. So they get us farther away from the thresholds, are kind of like more negative. Okay. So finally, that's fine. This is what we're talking about today. But we mentioned this at the very beginning of the potentials. So the reason I'm asking you, okay, what happens if a positive ion flows in, depolarizes, more likely to fire off an action potential? You're also going to say, when we describe that this is exciting the neuron. It's excitatory. So the excitement is that likelihood that you're going to fire off an action potential. You're getting it closer to firing off an action potential, more likely to fire it off. So inhibition would be the opposite. So if we have hyperpolarization, make it harder to off an action potential. That would be inhibitory. You'd be less likely to fire off. And those are terms that we're going to be using today. So that's why I wanted to start out by linking them together in our brains. Okay? Depolarization and excitement, excitatory potentials are really going to be kind of the same thing. Inhibitions and hyperpolarizations also kind of tied together. Excellent. All right. Bunch of people. Okay. So the information, those graded potentials, those small changes to our membrane potential happen because we have a stimulus come in, but now we know that stimulus is pretty likely a neurotransmitter, right? It's going to bind to an ion channel. So that was our receptor on our postsynaptic. The receptor receives our neurotransmitter, right? And eventually a channel is going to open. Our simplest are when we have just ligand-gated ion channels. In that case, our neurotransmitter is our ligand, binds onto the channel, and opens. And then depending which ions move, we have a change to the membrane potential, either going up, depolarizing, excitatory, or going down, hyperpolarizing, inhibitory. Okay? So this depends on which channels we ultimately open and the direction of flow of those ions, which is why we spend so much time thinking about the driving forces on different ions. So for sodium and calcium, the electrochemical driving force points into our neuron. So if we open a sodium channel or a calcium channel, we have positive charges come into the cell. We saw that during our action potential. And then on Friday, we saw that when we were talking about neurotransmitter release, that calcium coming into the cell is the trigger for our synaptic vesicles to bind to the membrane potential, to bind to the membrane of our presynaptic neuron and then open up, releasing that neurotransmitter. Okay. So opening a sodium channel or a calcium channel is going to create a graded depolarization that is excitatory. So we are now going to call that, when we're focusing on specifically that postsynaptic neuron, right? We're going to call it an excitatory, because we're getting more likely to get to threshold and fire off an action potential. Postsynaptic, because we're talking about that postsynaptic neuron. So that neuron after the synapse that's receiving our signal is the postsynaptic neuron. Okay. And it's a potential because it is a change in charge. So it's related to our membrane potential. So the abbreviation here for an excitatory postsynaptic potential is an EPSP. Okay. We got excitatory, we got postsynaptic or PS, and then potential is that final. Okay, so all this is saying, we're describing that we created a change in the membrane potential that makes that postsynaptic neuron more likely to fire. And we can have the reverse. So we open a potassium channel. We know potassium wants to leave the cell, right? When it leaves the cell, it hyperpolarizes. When we're hyperpolarized, we're farther away from threshold. This is inhibitory. We're less likely to fire off an action potential. So we name it the same way. So its effect is inhibitory. The place where we're focusing is that postsynaptic neuron. Right, so the neuron receiving the signal is the postsynaptic one. And potential, because we're talking about that change in charge. So an IPSP, an inhibitory postsynaptic potential, is one where we're less likely to fire off an action potential. This usually comes from opening of potassium channels or opening of chloride channels. The situation with those chloride ions is a little complex. It can either hyperpolarize the membrane or just kind of stabilize it and cancel out any positive charges that come in. Okay. So So I would focus on the potassium because we've talked an awful lot about potassium. If you want to focus in on that idea of what an IPSP is. Okay. So when we are thinking about these postsynaptic potentials, these PSPs, either EPSP or IPSP, we're focusing on when that postsynaptic neuron receives a neurotransmitter, right? So it has its receptor, it's catching the neurotransmitter that's been released by our presynaptic neuron. When we bind that receptor, we have a change in the processes inside that postsynaptic neuron. We can just directly open a channel if we have a ligand-gated ion channel, or we saw our more complicated receptors that are linked to our G proteins. So we could take a couple more steps, but eventually we're still going to either open or close an ion channel in order to change our membrane. So for excitatory postsynaptic potentials, our most common neurotransmitter that creates an excitatory postsynaptic potential, so the most common neurotransmitter to get us to fire more action potentials more often is something called glutamate. So glutamate is a neurotransmitter, usually excitatory. The reverse, our most common inhibitory neurotransmitter is GABA. So when GABA binds onto those receptors, usually that's going to create inhibition, which means we're creating some kind of hyperpolarization. Right, so we're either letting potassium leave the cell, or we're letting chloride ions, those negative. Definition of excitatory is that we are more likely to produce an action potential. And this happens when we have depolarizations. Graded potentials that are depolarizations, got us closer to threshold, more likely to fire off an action. Inhibitory is the reverse. So hyperpolarizations take us farther away from threshold. We're less likely to fire off an action potential. Okay. The other thing that can happen with inhibition, slightly more complicated, involves chloride ions. You can stabilize membrane potential. So we saw that fluoride equilibrium potential was kind of down near arresting membrane potential, so below threshold. So depending on exactly where we are in terms of resting membrane potential and that range up to the threshold, or it might move either direction, but it's going to keep you below threshold overall. So here we are looking at some examples of excitatory postsynaptic potentials. Okay. On this, we're looking at a neurotransmitter that binds in to an ionotropic receptor. So this is a ligand-gated ion channel. This one happens to let both sodium and potassium move, but we know that that force for sodium to move into the cell is really strong, right? Because we're far away from that sodium equilibrium potential. So the overall effect here is going to be that lots of sodium moves into the cell and a little potassium. So lots of sodium in means we're depolarizing, getting closer to the threshold. If we have enough of these open, we might hit threshold, then fire off an action potential. So that's one way we can do this. And we can see that measured right here, right? So you can see that positive change, that depolarization, that excitement. Now for a slow response, but in the same direction, so still excitatory, okay? This whole picture is more complicated, but we still have a neurotransmitter binding to a receptor on our postsynaptic neuron. This happens to be a metabotropic receptor, so it has to activate a G protein, which then splits open. The cell has some internal signaling, so there's a second messenger system involved here. But ultimately, the effect of the neurotransmitter in this image is that we've closed a potassium channel. All right, so we've closed a potassium channel. Potassium usually flows out of the cell. Okay? Potassium can't flow out of the cell. Now we're keeping those positive charges trapped inside. So more positive charges inside excites that postsynaptic neuron, makes it more likely to fire off an action potential. So that's another way we might see a depolarization here. But there are many different ways different neurotransmitters can function. So many different types of ions where we can either open or close channels, many types of receptors and second messenger systems that can create differing effects in postsynaptic neurons, but we're always just focusing on, okay, is the charge inside that postsynaptic neuron going to go up when we do this? Depolarizing, excitatory, or is it going to go down? In which case we're hyperpolarizing, inhibitory. The big takeaway here. So taking a look at some inhibitory synapses, we see, in this case, for fast response, we have a neurotransmitter binding into a channel that moves only potassium, opening it up. Okay. So potassium leaves the cell becomes more negative. So this is a hyperpolarization. This is inhibiting that postsynaptic neuron, less likely to fire an action potential. Here on the right, we are again looking at inhibition here, right? So here we see complicated system going on with the chloride ions. So there are chloride pumps existing in a bunch of your cells, but we're going to focus here on this image of that neurotransmitter binding in, allowing chloride ions, negative ions, to enter this cell specifically. Okay? So if we have chloride ions move in, this creates an IPSP. Chloride can also stabilize membrane potentials. I won't expect you to know the full details of how it stabilizes, but just think about it as canceling out, basically like sodium ions, stuff like that. So just a chance for me to take a look at what your questions are at this point. Open up my phone and check in. So we can also think about this in flowchart form. So these EPSPs and IPSPs are gradient potentials. Okay. So we're thinking we got our presynaptic neuron with axon terminal. We got our postsynaptic neuron, axon terminal. Okay. So what we're saying is happening here. Okay, so say we have a higher frequency of action potentials. So like more action potentials coming down this axon, the presynaptic cell. As we have more action potentials, more charges kind of building up here, I'm gonna say we might end up with more neurotransmitter being released. Okay? Every time an action potential gets here, more calcium might come in, more neurotransmitter released into the synaptic cleft. Okay? If we have more neurotransmitter available, more of it is going to bind to the receptors on our postsynaptic cell. Okay? And here's where we would care about what those receptors are and what they do. Right, so they might open a channel, either letting positive charges flow in or flow out. They might close a channel, trapping those positive charges in, like we saw in that example of an excitatory postsynaptic potential that is trapped in potassium. Okay. So they are either increasing the permeability of that membrane to the ion that's opened a channel. So if we open a sodium channel, we say we increase the permeability of that membrane to sodium. We close a channel, close a potassium channel, we've decreased the permeability of that membrane to potassium, right? Which means that we have either more ions move if we increase permeability, or fewer move if we decrease permeability, right? And so overall, depending on our ions, right, we have hyperpolarization or depolarization. So hyperpolarization, usually we're just going to focus on the in direction. Potassium move in, or chloride moves in. We'll have hyperpolarization, so that would be our IPSPs. And if we have depolarizations on the opposite sides are going to be EPSPs. And we'll just focus on in and opening. All right, for the simplest version of this, we can keep it as simple for our purposes for this unit for right now. So we have coming in sodium or calcium. We're depolarizing and exciting that stuff. So this is the big picture of what is happening. Right, so these are graded potentials on that postsynaptic cell due to changes in ion permeability. So we have changes in the state of these different ion chains. For our excitatory synapses, we saw here before, here, right? But we're just talking about postsynaptic neuron right here. Our easiest way to create excitation is going to be if we have a sodium channel and sodium moving in, or if we have a calcium channel, the two over there as well, and calcium moving in. Right? So if we open these channels, this is the direction these ions will flow. Extra bit from that previous example was that if we close the potassium channel, potassium gets stuck and can't escape. All of these are examples of things that would cause excitatory postsynaptic potentials. Take an example. Okay, so for neurotransmitters, it's probably familiar to us, is the neurotransmitter serotonin. Serotonin does a bunch of stuff, but one of the things it does is bind to something called a 5-HT3 channel receptor. One of the things that that receptor does on net is to allow sodium to cross a cell membrane. I want you to tell me whether this would be an excitatory postsynaptic potential in that neuron receiving the serotonin, or would it be an inhibitory postsynaptic potential when you receive this serotonin signal? Awesome. All right, sodium came in. When we bound serotonin, excited. This is an example of what's going on with fluoride. We're going to skip the exact situation with fluoride, but you can see how what's happening here in these two examples is that it's inhibition, but it's not causing a dip on either of these pictures. It's really just causing a flat line when it's interacting with other components of this. So next, we're going to move into the idea of neural integration. The reminder about all our ion channels that we've been talking about. You've seen this slide before, okay? But we had our leak channels throughout the neuron. They're what was responsible for creating that resting membrane. They're always open. There are more of them for potassium than for sodium. Our neuron overall has greater permeability to potassium, which was why we are down at -70, which is pretty close to potassium's equilibrium potential. Jumping down, we talked about a number of voltage gated channels as we were talking about our action potential. So we had sodium channels that open, allowing sodium to flood into the cell during the depolarization phase of our action potential. Right? Voltage gated channels are why we care about getting to threshold, because the threshold is the number at which these voltage gated channels start to respond. Right? So those sodium channels open up, their activation gate opens, sodium floods in. Then there's a time delay, but those inactivation gates on that same sodium voltage gated channel swings close, stopping sodium from moving in anymore. Around that same time, a voltage gated channel for potassium is opening. So potassium starts leaving that cell, repolarizing the neuron. And that's essentially how our action potential works, right? So we find these voltage gated channels throughout the neuron, but mostly we see them in the axon, where we're transmitting that action potential, and especially in the axon hillock, which is that beginning part of the axon. So responsible for our action potentials. Our new voltage gated channel that we learned about as we talked about the synapse was our calcium voltage gated channel. So that's present in the axon terminal. And so we saw it labeled on our presynaptic neurons when we were looking at the synapse. Okay? When those calcium voltage gated channels open, when that action potential gets to the axon terminal, calcium flows in, and that tells that axon terminal that it's time to release neurotransmitter. So jumping to this one in the middle, final one, our ligand gated channels are opening and closing in response to things binding to them. So our ligands are things that bind. Now we know that mostly we're thinking about neurotransmitters here, at least in this context right now. And those are going to be located, those ligand gated channels, in the locations where we tend to receive signals. So mainly in the dendrites and the cell body, where we have those synapses with our presynaptic neurons, right? So we had those axodendritic connections, the axon terminal of the presynaptic cell to the dendrite of the postsynaptic neuron. We had axosomatic connections possible as well, so from the axon terminal of that presynaptic neuron to the soma or cell body of our postsynaptic neuron. Big summers. So now we're going to be talking about integrating different signals, right? So we can do a bunch of stuff with our neurons. We're not always just two in a chain. Really, when you think about thinking, you're getting a lot of signals from a lot of different places. Neurons are wired together in complicated patterns and complicated nets, and they all kind of affect each other. Okay? So we're going to have to put together a bunch of things to figure out what the overall reaction is going to be. Want to remember just our baseline, right? Our ultimate thing that we're trying to figure out is, do we have an action potential or not from our postsynaptic neuron? Right? We're going to be talking about adding in all different types of signals, but overall, we just want to know, are we firing a signal out to the body or are we not firing a signal out to the body? Okay. So the action potential in that postsynaptic neuron is going to be triggered if that membrane depolarizes to thresholds. If we don't depolarize to threshold, nothing happens, no action. We already know. Now we're focusing in on what can happen. Okay. So we can have some kind of complicated connections between our neurons. So thus far, we've just been focusing on one neuron that signals to another neuron. So we were just focusing on one synapse. But we can see that this isn't always the real anatomy of our nervous system. So in this case, you can see one presynaptic neuron that has many axon terminals, so many diverging signals. Okay. So this is showing us divergence, meaning that when we have one action potential come down this axon, it's going to tell all four of these whole neurons fire if it's excited. Right? So we're sending the signal to multiple different places. So that's divergence, when we take a signal and spread it out to a bunch of other neurons. And we can have the opposite. So when we have convergence, so a bunch of things coming together, here we're looking at a single postsynaptic neuron. Right? We can see that it also has a lot of synapses, but the place we're seeing all those synapses here on the dendrites and the cell body. So it's got tons and tons of signals coming in, kind of fighting as they tell this postsynaptic neuron what to do. So that's convergence, many neurons coming together to signal one common postsynaptic neuron. We're going to be thinking about that second example a fair bit when we think about whether a neuron is going to fire. So we want to remember graded potentials can sum, we can add them together. And our IPSPs and EPSPs are graded potentials. So if we are looking at a single postsynaptic neuron here, right, that is experiencing the convergence of many different presynaptic neurons. And so we got 1, 2, 3 signals coming here. This is why we care that we can add together signals, right? This is why we care about summation. Right. So what we can see here in this example, we're looking at what happens with temporal summation. So for A, this little figure of voltage on the membrane potential, we're just looking at what happens if A fires once, fires twice. If they're slow spaced like that, we might not get up to threshold. But if we fire them up fast together, we stack them on top of each other, we can depolarize the threshold and set off an action. As we are looking at these diagrams of neurons, I want to point out we have some common color coding, right? So we have colored all the excitatory connections causing excitatory postsynaptic potentials in green, okay, and all the inhibitory ones, so taking us the opposite direction, in red. So inhibitory postsynaptic potential here is C. So we can see some of that happening here in our diagram B. So first, we see what happens when A fires. So when A fires off a neurotransmitter, creates an excitatory postsynaptic potential. Right? So that's what happens if we have just A. If we have just B, B is also excitatory. Right? So if B is firing alone, Same deal, we see a little rise in our membrane potential. But C is different. So C is inhibitory. Right? So an inhibitory postsynaptic potential. So if C fires by itself, we see a drop in that membrane potential. So we see this little hyperpolarization there. So if we are talking about summing together action potentials here, summing together these stimuli, you want to know which neurons are firing. Are they firing together? Are they firing separately? So this next time point, A plus B, is showing us what happens if A and B fire at the same time. Okay. So if A and B fire at the same time, we'd stack these two graded potentials on top of each other. So these little mini depolarizations in this example are getting us to threshold. And so we're firing off an action. That's what we see happening there. However, if instead we see A fire not with B, but instead at the same time as C, A was causing excitation, depolarization here. Okay. But C is inhibitory. Okay. We still have to add them together if these two fire at once. But when we do that, we can see that they're canceling each other out. Okay. When we have this excitatory postsynaptic potential, this excitatory synapse firing at the same time as we have this inhibitory synapse, we may not see any effect at all on that membrane potential, right? So they might cancel each other out. So when we're looking at convergence and we're looking at whether or not that postsynaptic neuron fires or not, we have to pay attention to each of those synapses. Is it excitatory? Is it inhibitory? And that timing, are they firing at once? Are they firing separately? To add them together. We're not going to be doing real math. We're just doing little ideas of positive and negative canceling each other out. There's no real numbers are going to be involved here, other than a resting membrane potential, our threshold, and then could be action. When we think about something called frequency coding, right? Frequency coding has to do with this idea kind of the temporal summation, right? So the degree of depolarization in the axon filament, that postsynaptic neuron, can be affected by how frequently action potentials are. Right? So we're going to sum together different effects. So summation is affecting the depolarization. And that summation can therefore influence how frequently an action potential fires. Right? So when we have more action potentials coming down, more neurotransmitter gets released. And therefore, we can have a greater effect on our postsynaptic neuron, depending on the neurotransmitter of the receptor, can be either inhibitory or excitatory. But I'd like us to think more closely about is modulation. Okay. It's probably carry us over, but what we can have happen is we can see a situation where we have a presynaptic neuron, a postsynaptic neuron. We have something almost like convergence happening here. What we can see is the third neuron. It's not coming in separately to that postsynaptic neuron. What we see instead is that the modulating neuron is jumping in the end of this connection with the presynaptic neuron. So it's jumping in here, and we can see what we would call an axo-axonic synapse, because it's between the axon terminal of this neuron and the axon terminal of this neuron. Okay. So they're coming together here at their end. What can happen then is that this connection itself that we're looking at before our main synapse can affect how much neurotransmitter that presynaptic neuron releases. Okay. We'll take a look at this. Looking at this chart, we are seeing here neuron D has an axosomatic connection to neuron X. So does neuron C. And we can see their effects down at the bottom. So if C fires, creates a slight depolarization. D fires, creates a slight depolarization. But modulator neuron E isn't connecting to X. We're looking at an axo-axonic connection between E and C. So the synapse of E, actually they're on the axon terminal of neurons. So E isn't affecting X directly. So when E fires alone, nothing happens to that membrane potential of neuron X. So this is showing the membrane potential of X. And nothing happens if E fires alone. But if we have C and E fire together, something green because they're both excitatory. And when C fires alone, you get just a little bit of neurotransmitter. But when C and E fire together, you get lots and lots of neurotransmitter. We can see that that connection between C and E depolarizes us to threshold, and we do see an action. When E fires along with D, there's no connection between D and E. So the peak that we see when D and E fire together is just that same peak that we saw for D alone. Pick up here next time and think about what happens when the synapse is inhibitory. The next time I'll do a combination, a little bit finishing up this modulation and a little bit of